Hello, and welcome to this introductory video about Taylor polynomials, Taylor series, and Maclaurin series. And this is for section 10.7 and 10.8 in our calculus text. And so we've been talking about series a whole lot, and we've recently talked about power series. And we even found a power series representation for one function, 1 over 1 minus x. And so what we want to do is we want to expand our capacity to find other power series representations, but we're going to do that through the idea of trying to identify, given a function, we're going to start off by thinking about, well, if I had a polynomial of finite degree, what would be a good polynomial approximation to the function that I've got on hand? And we're going to be looking at, thinking about e to the x, cosine x, sine x, and so we want to think about how can I come up with a decent polynomial approximation for that. So we're going to start by thinking about expanding, writing a polynomial in terms of powers of x minus a. You can see here in this first sentence, and we'll see the payoff for doing that in just a few minutes. But we're going to take a polynomial and write it as t sub n equals c0 plus c1 x minus a plus c2 times x minus a squared, c3 x minus a cubed plus c4 x minus a to the fourth, dot, 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 dot. And if it's an nth degree polynomial, the final term will be c sub n x minus a to the nth power. So we can take any polynomial and write it in terms of powers of x minus a, where a is any constant, any point in the domain of the function. And so the big question before us is, how are we going to determine these coefficients? What is c sub 0, c sub 1, c sub 2, etc.? So we want to try to figure out, can we find a formula for these coefficients? And it's probably going to involve a, it's probably going to involve my function f of x. And so we'll see, this is what we're going to be working toward in this video. So how can I accomplish this goal? So I'm going to erase all this. How do we accomplish this goal? Well, we're going to make some important assumptions. And I think these are very reasonable assumptions. And those are that the polynomial and the function are going to behave as similarly as possible at this point that we're expanding about x equals a. And so let's think about what does that mean? Well, it seems like maybe the two functions, the polynomial and the function, should have the same value when I plug a in. And maybe they should have the same slope at a. And maybe they should have the same amount of concavity at a. And since it's an nth degree polynomial, we can go through and do that through the first n derivatives. Because the nth derivative of this nth degree polynomial will be a constant. But beyond that, our derivatives will be 0. So we can only go through the first n derivatives. But it seems like perhaps that the polynomial that we're seeking and the function that we've got on hand should have those same properties at x equal a. Now we're going to take these equations, which I've numbered 1, 2, 3, 4, etc., and look at the form of t sub n, and we'll actually be able to see that we can find out what the coefficient should be in terms of the function. So the idea is that these values are all computable. So we've got a function, we can stick a in, we can calculate its derivative, we can stick a into that, we can take the second derivative, stick a into that. So these are all computable values for us. So now let's see what we can do toward this end. So I'm going to start with equation 1. And I've got T sub n of A equals f of A. So on the one hand, what is T sub n of A? Well, this is where writing our polynomial in terms of powers of x minus A really work out well. So let me come back up here. T sub n of A is going to be C0 plus C1 times 0 when I put in A for x, plus C2 times 0 squared, plus C3 times 0 cubed, etc. So I'm just getting a bunch of zeros here except for the first term. And so T sub n of A is equal to C sub n. But we've also said that we want T sub n to be, try again. This is C sub 0. So T sub n of A is going to be C0. But if T sub n of A is equal to f of A and it's equal to C0, that tells me that C0 is simply going to be the value of the function. So there's our first formula. Second of all, the derivative should match. Well, let's figure out what T sub n prime is. And again, I can go up here, erase this. What's T sub n prime? Well, it's a polynomial. We can use the power rule to calculate the derivative. The derivative of a constant C0 is equal to 0. The derivative of C1 times x minus A is just going to be C1. The derivative of C2 x minus A quantity squared, well, I can use the chain rule. I'm going to get 2 times C2 times x minus A to the first times the derivative of x minus A, but that's just 1. That's convenient. The next one I'm going to get 3 C sub 3 x minus A squared times 1 plus 4 C sub 4 x minus A cubed times 1, dot, dot, dot. And over here at the end, I'm going to get n times Cn times x minus A to the n minus 1. So I'll write that down here so we don't have to keep referring up to the top. And so when I plug A in, I'm going to get C1 plus a bunch of zeros. But I've also said that I want, that's Tn prime of A is going to be C1, but T1 prime of A is supposed to be F prime of A, and so there's my second coefficient. C1 is F prime of A. Now let's look at equation 3. If Tn double prime of A needs to be F double prime of A, well, I can calculate T double prime of X. Derivative of C1 is equal to 0, so I'm going to get 2C2 plus 3 times 2 C3 times x minus A plus 4 times 3 C4 x minus A squared. And then at the end, I'm going to have n times n minus 1 Cn x minus A to the n minus 2. And so Tn double prime of A is just going to be 2C2. But on the other hand, we want it to be F double prime of A. And so that tells me that C2 is going to be F double prime of A divided by 2. Let's keep going. Our fourth equation is Tn triple prime of A equals F triple prime of A. The third derivative is going to be 6c3 plus 12 times 2c4 times x minus a plus dot 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 n times n minus 1 times n minus 2 cn x minus a to the n minus 3. And so Tn triple prime of A is going to be 6C3. But on the other hand, we want it to be F triple prime of A. And so that tells me that C3 is going to be F triple prime of A divided by 6. And we can do one more. Maybe we'll begin to see a pattern. Our next equation would be that the fourth derivative at A of the polynomial is equal to the fourth derivative of f at a. The fourth derivative is going to start off with a 24c4 plus a bunch of other terms, and then I've got n times n minus 1, n minus 2, n minus 3, c sub n x minus a to the n minus 4. So the fourth derivative of t sub n at a is going to be 24c sub 4. On the other hand, I want it to be the fourth derivative of a, and so I get that c4 is equal to the fourth derivative of a over 24. So let's just assemble these and see if we can begin to figure out what the pattern is. So again, c0 is f of a, c1 is f prime of a, C2 is f double prime of a over 2. C3 is f triple prime of a over 6. C4 is the fourth derivative at a over 24. Well, maybe we're beginning to see what's going on with these denominators. 2, I could rewrite as 2 factorial, 6 as 3 factorial, and 24 as 4 factorial. And if I come back up here and say that's a 1, 1 is equal to 1 factorial. And if we agree that 0 factorial is equal to 1, I could think about this as 0 factorial here. So let me replace this, and this with 2 factorial, 3 factorial, 4 factorial. And so perhaps we're beginning to believe that c sub I is going to be the ith derivative at a over I factorial. And this is in fact what's going to happen. That's what these coefficients should be in order to have the nth degree polynomial match up with the function that I've got on it at hand through its first n derivatives. And we call this result the nth degree Taylor polynomial. And so t sub n is going to be summation I equals 0 to n, the ith derivative at a over I factorial times x minus a to the I. That's the nth degree Taylor polynomial for a function centered at a. If we let n go to infinity, we get what's called the Taylor series. And so we would say that f of x is summation I equals 0 to infinity, the ith derivative at a over I factorial times x minus a to the I. And so the Taylor series is what we might call an infinite degree polynomial representation of the function, or it's our power series representation for the function. So we can find the coefficients by taking the derivatives, successive derivatives of the function, evaluating them at a, dividing by the factorial that we're currently working with, and then multiplying that by x minus a to that appropriate power. Special case, and the one that we're going to be focusing on almost exclusively at this point, is the case where a is equal to 0. And so if a is equal to 0, we get what's called the Maclaurin series expansion. So it's going to be summation I equals 0 to infinity, f, the ith derivative, evaluated at 0 over I factorial times x to the I. And this is the big one that we're going to be dealing with and addressing some examples in a class session.